Welcome everybody to the Planetary Simple Science Seminar Series. Today we have Zach Sharp, who is a professor here at the University of New Mexico. He works at the Center of Stable Isotopes, and he's also part of our CASA Moon team. So we're super excited to have him here to be talking about how we basically form planets. So Zach, let me get this set up for you.
All right, well, I hope you're all able to hear me, and thanks for coming. This is a special day because we have pizza at our seminar, which is very exciting. And I'm honored because before it's been bagels, but they're not here, which means that I'm not going to get any pizza. That's a little bit of a bummer, but okay, you don't care about that. You're in another part of the world. Here's my talk today. It's Forming Earth by Pebble Accretion, and also why we have a habitable planet. This is work that is a collaborative effort by myself, Peter Olson, and our PhD student, Susmita Garai, who is here in the audience. So I'm giving an outline. I don't necessarily like outlines, but there's a lot that I'm going to be talking about, and I just want to give you a quick overview of what we're going to be talking about. We'll start talking about impact accretion, the kind of generally accepted paradigm for how planets are made. And I will come to the conclusion that you can't make Earth with this. What do I mean by Earth that's purposely ambiguous? We'll get back to that. And then I will offer as an alternative idea of pebble accretion, which has been around for maybe a decade and is just starting to get real kind of noticed by the terrestrial planet community. I'll talk about what that is. I'll show you that we can make Earth's major element composition by the process of pebble accretion, and that it satisfies a bunch of geochemical constraints, including nucleosynthetic isotope anomalies, tungsten hafnium isotope data, siderophile element abundance of the Earth. We explain the sources of Earth water and also the source of Earth's helium. So here we go. Impact-based accretion model. We can attribute this to several authors independently, Victor Safronoff and George Weatherall. And the basic idea for the impact-based accretion is this. You have bodies that are like bumper cars flying around in the solar system, colliding into each other, merging into larger bodies, and ultimately making the planets. So the quick scenario for how our solar system is made by this mechanism is that we start with a molecular cloud. This is our stellar nursery, consisting predominantly of hydrogen and helium gas, but obviously containing all of the elements that we need or that exist in our solar system today. It is shocked, perturbed by something like a supernova, nearby supernova, which causes the collapse of the molecular cloud, which happens really quickly. And during this collapse, there's a big change of potential energy, so temperatures rise as high as maybe 2,000 degrees. And then in a very short time, years after that, we start having cooling and the coalescence of dust grains, which then merge to form larger bodies, planetesimals, kilometer-sized objects on the order of hundreds of thousands of years. And these continue to make planetary embryos. Now we're in greater than 1,000 kilometer size. And the definition of this is that these are large enough that they actually will gravitationally attract nearby objects. They are going to ultimately merge into our protoplanets and then our planets. And this is occurring on a time scale of tens of millions of years. The last thing that happened, at least with regards to Earth, of course, is the giant impact. The timing for this is not precisely known. Estimate of, let's say, 30 to 150 million years after the beginning formation of our solar system. This was nice because it actually took two bodies. Here, the proto-moon Theia is shown to be much smaller than Earth, but two bodies that may have even been close to equal size and mass, and merged them into one, where we now have a smaller satellite rotating around a larger one. The problem with this horrible giant impact is that it just destroyed all the geochemical evidence for things like timing and sources that existed before. So in that sense, it's really bad, but at the same time, you know, there's some good stuff about the moon. For one thing, we're all here because of the moon. So that's our impact-based accretion model. And It has been proposed by many authors based on geochemical arguments, isotopic arguments, that chondrites may be the building block for the Earth and the Moon. Chondrites being primitive meteorites that contain chondrules, chondrules being these small, I guess I really don't have I have flips. Small round objects that occur in them, they are thought to be liquid droplets that occurred in the solar nebula. They've coalesced into these bodies, old primitive bodies, and it's thought, okay, this could be what has formed Earth. In particular, enstatite chondrites are thought to be a really important component of the Earth because their oxygen isotopes match Earth, and a lot of nucleosynthetic anomalies also are consistent with enstatite chondrites. So here is a classic figure from taken by Paul Warren. In 2011, we're plotting chromium versus titanium isotope anomalies. All of the carbonaceous chondrites plot way up here. Enstatite chondrites, other primitive achondrites plot down here. And the Earth and the Moon are close to this enstatite chondrite range, and therefore it's been, I say, generally accepted that enstatite-like chondrite materials are necessarily a significant component of the Earth. So it all sounds good, but there is like an issue, which we'll see in a second. This is Susmita's work. She took the average chemical composition of iron meteorite, carbonaceous chondrites, enstatite chondrites, ELEH, and ordinary chondrites, mix them together in proportions to most closely match the bulk chemical composition of the Earth. So these 7 elements, iron, nickel, silicon, magnesium, calcium, aluminum, oxygen, making up like 98%, is that right, Susmita, of the Earth's mass? Doing a least squares to see how we can best fit Earth by combinations of these. And here's the results. You can see that it's least squares, Monte Carlo, give similar answers. 87% enstatite chondrites, 6% C chondrites, and then 7% iron meteorite. So that would appear, based on major elements, to be what the Earth is made of. But there is a problem with this, and it is that the fit to Earth's assumed composition is really not good. In fact, it's well outside of the uncertainty of the Earth composition. On the x-axis, we have the elements, the major elements. On the y-axis is the misfit in percent between our calculated best fit value and the actual Earth value. The assumed Earth range, the uncertainty of the Earth range, is shown by the blue bars here. So for virtually every element, you don't get a good match. Some are above, some are below. We can change the compositions, but we can't really get a better fit than this. It does work pretty well for the nucleosynthetic isotope anomalies for chromium and titanium. The Earth value close to 0, and our best fit in least squares is relatively similar, maybe off a little bit in titanium. But the major elements don't work for Earth. And this is something that is maybe a bit surprising. I've talked to lots of people about this. It's like, isn't this a problem? Like, we talk about, well, what about tungsten 57 or whatever isotopes? The major elements should be as fundamental as anything. We know for these elements what the Earth's composition is really well, and yet we cannot match it with the most common chondritic meteorite types. It doesn't work. Okay, so we are going to turn to an alternative planetary formation mechanism as a way of evaluating this further. And this mechanism is called Pebble accretion. Pebbles, things like chondrules, small millimeter-sized objects that exist in a nebular disk will orbit at a sub-Keplerian velocity, resulting in a radial drift inward and then captured gravitationally by a growing planet. What does this mean? How does this work? By the way, the pizza's coming, so you guys get up and you can enjoy it. How does this work? Well, here's an example. Whoops. there. All right. So this computer animated generation image just shows dust in a box, right? And we all know from experience, with time, the dust will settle down to the bottom of the box. But the gas in that box will not settle. Even though it's being attracted gravitationally by the Earth, it remains in the box. And the reason is because there's an outward pressure of the gas. Gas has a pressure, and so it will remain in suspension, whereas the dust is going to settle back down to the Earth. This is happening, you know, in a nebular scale. The gas that's rotating around the Earth is rotating in a sub-Keplerian orbit because of this outward pressure. The small particles that are within that gas experience the drag of the gas and therefore rotate at the same speed. So they're going slower than what would be necessary for them to be in a stable orbit. And therefore they're going to be drawn in towards the sun. And the rate of transfer into the sun is really quite rapid. This shows a animation by Chris Ormel of this process. What do we have here? X, Y, the sun or the star is to the left. We have flow lines of the gas shown with the green, and because in this case, a large planetary body is in a Keplerian orbit, it's rotating around and it's in a stable orbit, so it's actually traveling faster than the gas around it, and it experiences a headwind of the gas. Outward of the position of that planet, the gas is coming towards the planet, at least from the reference frame of the planet itself. Inward, it's going in the other direction, and this has to do with the Keplerian shear of the nebula, where the angular momentum or the velocity of the angular momentum is more rapid closer to the sun than it is away from the sun. What we see are different sized pebbles as they're floating in the nebula. The largest ones being the yellow, the red are smaller, and the blue are the smallest. We're going all the way out here to the hill radius in the purple circle, and what you can see is that principally the yellow pebbles are drawn into this growing planet. The red pebbles are also drawn in, but not as much, and the really small blue ones, because they're so small, and they're really captured by the gas, are attracted less to the growing planet than the larger ones. So here is Susmita's work of showing the shear radius for different sized pebbles. If we're talking about millimeter sized pebbles, which is kind of what we would expect for chondrules, we have a large capture radius close to that of the hill radius of the growing planet, whereas really small particles, 0.01 millimeters, so this would be dust, it would be a matrix in a chondrite, you almost have to have a direct collision in order for these really small particles to be captured. And even then, because of the pressure of the gas around the planet due to gravity, they can sort of be deflected. And if you really inefficient capture of small material, but much more efficient capture of larger material. That's fundamental because it provides us with an efficient mechanism. A physical filter is what I wrote up there that will preferentially incorporate pebbles, larger bodies, larger particles, chondrule-like things, but the fine dust that would exist in the nebula is excluded from the growing body. Consider the difference between this and chondrites, where you have a mixture of both chondrules and dust that would be the building blocks, or the feedstock, as Tony would say, of our growing planet. So what do we need for pebble accretion to be effective? 3 ingredients. We first have to form a seed mass, something big enough to cause this gravitational attraction to occur. That has to happen fast while we still have the nebula present. We need a large population of pebbles in the nebula, and we need the nebular gas. If we're in a vacuum, of course, the present day vacuum of our solar system, then things are not going to be affected by gas drag. The seed mass, there are a number of of, theoretical calculations of this because, again, of the Keplerian shear that exists in a nebula where the angular velocity is more rapid, closer to the sun. We have shearing and turbulence, and we see here in a time series of what's happening for mass within a nebular gas. We have streaming instability. We start with nucleate material, and at this point, these circles represent near Hill radius diameter gravitational attractions. This occurs really fast. In the case of this paper, it's what's it called when you don't have unitless time. But in just 100,000 years or so, we can start to form these bodies that are large enough to start pebble accretion occurring. Do we have large populations of millimeter to centimeter sized pebbles in a nebula? So here's a bunch of photographs of young, less than 1 million-year-old protoplanetary disks from the Alma telescope in Chile. And if we look at the disk structure of this, the important thing here is that our size particles are on the order of millimeter size. Okay, and the density of the material is large enough so that we can form with the inner solar system mass and perhaps some outer solar system material that cross Jupiter's orbit enough mass produced by Pebble accretion to form the interterrestrial planets. Body by Pebble accretion, time on the x-axis in millions of years, the mass relative to Earth on the y-axis, and these numbers here are for different Stokes number. Millimeter-sized pebbles are shown, I guess, there. That's the kind of range of millimeter-sized pebbles within 1.5 million years, 1 to 1.5 million years. We're getting up to at least a half an Earth-sized mass. So this is really, really quick. I mean, just an order of magnitude at least faster than what we would expect from your impact collision models. And it's well within, I think, there's not a lot of argument about this, that the solar nebula will still be present as we get to this size. Now, we're not claiming that the planet is growing all the way to Earth size. In fact, we know Earth didn't grow to Earth size because it was smaller and we had a collision with Theia, which made it larger. Somewhere, in this range is probably the growth size of a planet by Pebble accretion. And after that, in later time, they collide together to make ultimately the planets that we have. So it can happen fast. And what happens when we use this Pebble accretion method then, which I would argue based on the previous discussion, is something that's almost necessarily should occur in a nebula. It's not just a far-flung idea. It's like, this should happen. Well, we can't make Earth with chondrites. Can we do it with the components of chondrites, which are our pebbles? So here, what Susmita is considering is AOAs, CAIs, these early refractory inclusions, as well as chondrules, and also metal grains. That would be free-floating grains in the early solar nebula. We do a best fit to see if we can match Earth's composition, and now we do just a great job. We have done this by least squares and Monte Carlo simulations to get the same answer, which is reassuring, as you expect to. And we have two different plots here. One is CMA. This is after some work by Connell Alexander, who estimated the composition of various end-member components using both measurements and also extrapolations and certain isotope ratios and a number of things to come up with his best estimate, and it works really well. You get a beautiful fit. The other one, the so-called CDB, what does that stand for?
Component database.
Component database, which is the actual measured composition of the components. Is that right? Yeah, and it's not quite as good, but still pretty darn close to fitting the Earth. This is the component fraction for that best fit. And what you see, which may be surprising and in fact a little bit discouraging based on what Paul Warren showed us from chromium and titanium, is that the majority, whether we have the CMA or the CBD model, the majority of material that's forming the Earth is C chondrules. We also have a large metal component, also AOAs, and then a little bit of CAI, some ordinary chondrules in the case of this one. So it is at odds with this, or it appears to be at odds. The Earth plotted here in these case of these nucleosynthetic isotopes, the Earth is at a closer to the andesite chondrites than the carbonaceous chondrites, right? So it appears to be a puzzle, but we're going to solve for the predicted epsilon 54 chromium, epsilon 50 titanium values from components rather than these, which are chondrites. Here's a paper by Williams plotting, these are chondrite data. And indeed, you see the non-carbonaceous achondrites and chondrites, the gray, they are much closer to Earth than the carbonaceous achondrites and chondrites. Quite a big difference. And it seems like we're not going to get a solution here. But if we look at the chondrule values, so not the bulk chondrite now, but individual chondrules, we have for the C chondrules, Allende and Grunda, there are a few different distinct populations. We have some here, yellow diamonds, which have a epsilon 50 titanium value about -1.5, and an epsilon chromium 54 about -0.5. There's also some populations up here. Okay, I mean they really vary, and we are using in our modeling these low ones down here. Why are you using the low ones? Well, for one thing, they worked, but also, and this is really the main reason, is that if we look at the achondrite data shown in yellow, highlighted in yellow for both titanium and chromium, the titanium values are all similar, -1.5. The chromium about -0.5. They are similar to this range here. And what we would argue is that these achondrites, they're really early formed bodies. They underwent differentiation because they formed so early that they had significant aluminum-26, and they underwent melting and differentiation. So the early formed chondrules, therefore, we would argue, are also going to have these light values. If we use those for our C chondrules, then here is our fit for the chromium and titanium isotopes, the major elements here, real good, and the chromium and titanium is essentially, a perfect fit to what the Earth is. Now, we can change these numbers, we can use higher input, and we'll get a different answer. But what we're showing here is that using a reasonable value for measured chondrule compositions, we can fit these nucleosynthetic anomalies. In spite of that, so many people like echondrites as a source to Earth, inner system source. Susmita went ahead and said, I'm going to force the echondrites to be 60%. We could have made it 70, 80. Once we get up to higher numbers, it gets worse. But with 60% echondrules, how well do we fit the Earth? Well, in that case, it's mostly echondrules, a lot of metal, a little bit of AOAs, the CAIs, no C chondrites, right? No ordinary chondrites. So this is with 60% echondrules, and here's the fit. It's not as good as with the C chondrites, but it's, at least for the CMA model, it's not terrible. This one's really not very good. The fit to the chromium and titanium isotopes is not as good, which is really a surprise. And this is not a really rock solid conclusion because we can also modify the composition of the echondrules. We just don't have enough data at this point. But it works with the C chondrules. Just for comparison with the previous studies, We have the classic studies from Anders in 1977. That's here, where he's using components, and then a Burbine and O'Brien study here. And again, our fits using chondrules in the Pebble accretion scenario gives us the best fit to Earth. All right, well, that's all good, but when we try to present this stuff, you say, well, what about? So it's a new idea. It's really different from the existing paradigm for how planets are forming. And while that existing paradigm is mature, and people are talking about a single isotopic system or elemental system to see how that fits in, because we have something that's relatively new, it's like, well, what about everything else? And that's something that will proceed as we move forward. But we have looked at a few other geochemical constraints on Earth to see if it fits in with the idea of Pebble accretion. So here is Peter's work, happening in constant evolution with Pebble accretion during Earth formation. He goes through a series of events that occur. So in the beginning, we have our pebbles forming, no core because we don't have differentiation yet. We reach a point where the body gets large enough, has gotten hot enough due to all of this potential energy release from the input of pebbles falling into it, as well as aluminum-26 decay. We form the core at this point. The mantle size goes down, of course, because some is going to the core, and they continue to grow over a period of 6 million years. And then you can look at this, the concentrations, mantle tungsten concentration drop way down when we start to form the core, rise again. After that, we can look at the epsilon tungsten numbers in this short time range. Here we are only at 5-6 million years. Going out further, now we're going to 100 million years on the x-axis. We have this initial Pebble accretion phase. And then in the simple case where we're taking two equal sized bodies that form early, half Earth size, and then sometime later, what is this, 95 million years later, we have a single giant impact. And when we look then at the tungsten isotope data, we see that we have an epsilon tungsten that goes up, and then after the giant impact, again, this depends, of course, on the degree of its equilibration and everything else, but it falls back to the early mantle predicted values. So it kind of works for equal-sized impactors. We also looked at it for arguably the more reasonable case of continuous impactors. So in this case, what we have is our early Pebble accretion phase, and then a series of large impacts, and then a giant impact. In this case, we got up to 90% Earth size and had a 10% impact size. And the tungsten anomaly jumps up and down as you have these big impacts. Large impacts, then finally the theta impact. And again, for Earth, the tungsten anomaly matches the Earth. And there's other conditions in between. What we learned from this study is that we absolutely cannot make Earth without having that giant impact. We also looked at siderophile element partitioning. Siderophile elements. So for this, Peter has looked at, say, 4 stages of planetary growth. In the first stage, it's the accretion of material, but it's not hot enough to melt. So we just have a homogeneous distribution of material. And then in stage 2, we start to get melting in the deeper parts of the Earth. And at this point, we have, because we have melting, we have the formation of a core. As the planet gets hotter, the melt zone moves up to the surface. So we have a silicate melt, a partial melt, and then the core. And ultimately, stage 4, the entire mantle is melted. We have a magma ocean and a core. Then we look at, here's the temperature pressure distribution of our planet. Pressure and temperature at the point of equilibration between the mantle and the core. Well, we see the pressures and temperatures going up in stages 1 and 2 as things get hotter and the pressure of the formation is higher. And then we have reached stage 3, that's where we're melting up to the surface. And so now the pressure drops all the way down to 1 bar. It's occurring at the surface. The temperature also drops because it's occurring closer to the surface than deeper. And then we move through stages 3 and 4. The important thing here is that the partition coefficient for these different elements changes wildly as we go through these different stages of planetary growth. And what Peter's done is to model for a growing planet what the distribution is. Okay, all right, we have 2 conditions here. One where we have growth of the bodies followed by a giant impact. And one of them is with 0.9 and 0.1, so that's a big proto-Earth, a small Theia. The other is 60-40, about the same size. And you can see that for the near equal size for the 2 bodies, we get a much better fit than if we have a large proto-Earth and a small Theia. So it's suggesting that the giant impact was near equal size bodies. Also for the core. The core estimated compositions, of course, I don't really know how we know these. It partly depends on the distribution, so it's a little bit of a bootstrapping, but our best fits were, let's say, a 60-40, again, match within the uncertainties of what we believe the core siderophile element concentrations to be. So it's working for that. Whoops. And I want to put this then all into a timeline, but first make this point about chondrites. This is the age of chondrules within chondrites. And whether we're looking at lead or aluminum 26 decay relative to the start of the solar system, we see that the chondrules within chondrites have a range of ages, and that they go all the way up to at least 3 million years after the start of the solar system. It means the chondrite parent bodies have to be younger than that, right? You can't incorporate something that's 3 million years old into a body that is older than it. So it's telling us that the chondrites themselves, because they have young, meaning a long time after the start of the solar system, a long time in 3 million years, the chondrites didn't form for several million years. We have very few chondrites at the, well, here's some there. Fewer chondrules that are really, really old, and a peak of these in, let's say, 1 in 3 million years. Couple things about this. First of all, chondrules are continuously forming. They didn't all form in the beginning. They're forming over this period of millions of years, 3 million years, when we have the solar nebula present. And while this is considered really old, if you're an impact guy, where you have things happening on the tens of millions of years time scale, for Pebble accretion, where Susmita and others have shown we can make a body in less than 2 million years, we're talking about Earth formation, or at least proto-Earth, in this region here, okay? So that leads to really some different ideas about the material that might have formed Earth, and then the other protoplanets, Theia, Venus, however many bodies went into forming that. So here's kind of a timeline then for what's happening early on. Let's say less than 1 million years, we have the formation of our planetesimal by some kind of instability. There it is there. And then we're having the refractory phases, the AOAs, CAIs, metal grains, and likely chondrules as well, that are forming near the sun. This was early. It was before chondrites formed. And so what does that mean? That means that these materials, they're not found in the inner system chondrites, or they're rare. So N-type ordinary chondrites don't have many of these refractory inclusions. They are found in things like CV chondrites, things that form way out. Presumably, these early form materials were expelled out to the outer part of the solar system and resided there for several million years before they were incorporated into a growing body. Whereas in the inner solar system, these early form objects are going to be drawn into the sun or captured by these growing planetesimals that are ultimately going to become the building blocks, the feedstocks for the terrestrial planets. They have proto-Earth, proto-Venus, this sort of thing. And so that material that exists in the inner system, planetesimals that are growing early, will become planets, are not incorporated in the non-carbonaceous chondrites, the N-site chondrites. Why? Because those early form objects either were incorporated in the planets or they were drawn into the sun. The only place we see them is in the outer solar system. And there could be a lot. I think it's 20%. Is that right? 20% refractory inclusions in some outer system chondrites. That is material that formed close to the sun, presumably, went out in deep space and was still concentrated at that high concentration. So it means that there was a lot of early formed material, and this is completely reasonable. It should be the case. Okay, then after this early formation of material for which we may not have any physical specimens, it may be incorporated into the earth, but we don't have any physical evidence of these early refractory grains other than what we have out here. Now we get into the main phase, the seed mass for our protoplanets, for the Pebble accretion have gotten large. We're Mars size and larger, and we're producing lots of chondrules, continuing for several million years. Right? We continue because we have the age of these things. The chondrule production continues over this time. We're going to be making some chondrules continuously, and we're assuming that some of the material from beyond Jupiter is passing over this barrier and getting into the inner solar system, making carbonaceous chondrules. Evidence for this, based on modeling, is seeing that there's some 5%, maybe 3% material that crosses past Jupiter's orbit. Doesn't sound like a lot, but there's a lot of stuff out there. And so over the millions of years, it could be a significant contribution, little here, to our growing Earth. Chondrites begin to form in this period. How do we know? Because we're seeing the age of the chondrites based on the end age chondrules. So they start growing here and here. And then later on, the nebula disperses, and pretty much the game is over. We're going to end up with our big planets, which were formed throughout this time, but got critically some unique material that formed in the early times. And there's our various chondrites, and kind of done. This will then ultimately result in giant impacts of these early formed protoplanetary bodies. Okay, one more thing. And we're doing okay, yes. Terrestrial planet formation by Pebble accretion. Another thing that it does for us, it's a gift that keeps giving, is that it gives us a source of volatiles. So if we have accretion in a few million years within the lifetime of the nebula, something that is predicted by Pebble accretion, we will generate a deep, hot nebular atmosphere because of all the energy of accretion. Temperatures of the surface will be in excess of 2,000 degrees, pressures in excess of 100 bars. It's mostly hydrogen, of course, and helium, and this atmosphere will extend all the way up to big body and hill radius. So a giant atmosphere with a really high pressure. Under these conditions with the magma ocean, we're going to have huge amounts of ingassing of both hydrogen and other volatiles into the magma ocean. So here's Peter's work on the thermal structure of both the planet and the atmosphere. At the top, we have the progress of what's happening, an early high pebble density, which decreases with time. Pebble settling rate increases as the body's getting larger and the mass is getting bigger. Altitude above the surface, temperatures 2 million, 3 million, we're reaching 2,000 degrees at the surface of the planet. And in the interior, it's getting up to 5,000 degrees. we go from a solid and then a rapid progression into a purely melt-rich region, stage 4 of Earth growth, happening in, again, the first couple of million years. PT estimates here for a half Earth mass body, temperatures 2,500 degrees, pressures 200-300 bars. So really high pressures, and we can calculate the amount of material that is then dissolved into the magma ocean. It turns out the majority of it, even though we have a hydrogen-rich atmosphere, we do have a partitioning between, or an equilibrium between hydrogen and H2O. And a lot of it is going to be dissolved as H2O, even at the low oxygen fugacity of a hydrogen gas atmosphere. But for an Earth mass of 0.5, couple of years, we're, 5 oceans worth of water are dissolved into it. And this is within the range of some estimate for what we have today. That said, there's another source of water which we're beginning to explore, and it's this. Here's my attempt at AI. Okay, not very good, but what we have is our magma ocean, and we have a constant rain, like precipitation of pebbles through this. And if we accept that the temperatures in the atmosphere are reaching well over 1,500 degrees Kelvin, up to 2,000, then we have melting of these pebbles and interaction of the iron with the hydrogen gas. So the reaction is iron oxide in the melt, plus the hydrogen gas making iron metal and water. Susmita has been doing some experiments where we are melting the salt or a more ultramafic composition in an induction furnace where we have a flow of hydrogen gas through here. And we have a flame top with the roof blowing up. But what she sees is that in a short period of time, we're making iron filings here. So it's something that, given the settling velocity of pebbles, it's, what does Peter say, a couple of weeks or at least a couple of days, right? For pebbles to settle through this hot atmosphere, we can have a significant reduction of iron oxide to iron. This could be part of the core ultimately. And it also produces water, which add another dozen water by this process. And then we can also be creative in terms of what other kind of volatilization occurs, things like sodium or silicon or whatever it is you want. All right. And then the last thing is helium. This is it. Last thing I want to talk about is helium. How do you get helium into the deep mantle? We know it's there. We have helium-3, primordial helium, coming up in mantle plumes, high concentrations. And we talk about impact, generation of planets, or late accretion. I cannot see how with late accretion of a volatile-rich material, that material can get into the lower mantle. I mean, helium is a slippery, light element. Today, it's assumed that there's kind of subduction zone barriers to this. But it's hard to imagine how we can get helium into the deep mantle, let alone the core. And a solution for this is with this massive atmosphere, 200 bars hydrogen, 30 bars of helium, that I have a helium-3 but helium-4 as well. Primordial helium will ingas into the magma ocean and ultimately will exchange with the core itself. So we have, after the accretion, where we have the atmosphere, after that's gone, then we start to have degassing in a convective mantle. It's actually lost relatively quickly, as I'll show you in the final slide. And then the helium-rich core is going to transfer to the mantle, and that will continue to supply helium to the atmosphere through time. So when we go through the mass, we have temperatures and pressures. The end of the solar nebula is here. Temperatures decrease after that because we don't have this growth. We don't have the blanketing of the atmosphere. Our core, with mantle helium, increases to this point. It continues to increase to here because it takes millions of years for that atmosphere supplied by the solar nebula to erode away. The core helium continues to grow because it's exchanging with the mantle. So exagrams, petagrams, this is 1,000 times greater. And so the kind of scenario time before present, early on, our core to mantle ratio of helium, in the beginning, it's all coming from the mantle, rapid convection, it's hot, and with time, the flux from the mantle is decreasing, we're having more material transferred from the core to the mantle, so that we end up with a surface helium flux like this. This matches what we have today. It actually was back calculated this to kind of get the initial conditions, but it is a mechanism to supply helium to the Earth. I think better than impact accretion, and it explains our fluxes today. So in conclusion, our Pebble accretion has a lot of advantages over the traditional impact model for how to make terrestrial planets. First of all, it makes the Earth's major element composition, which I think is about as fundamental as anything gets. It explains happening in tungsten data, it can match siderophile elements, and it forms planets, or at least the planetary embryos, which ultimately will collide to make planets really quickly. Supplies Earth's water, other volatiles, which I didn't talk about, and it supplies Earth's helium, and therefore it allows us to have a water-rich body and makes the conditions for it habitable. I will end there. Thank you.
Thank you so much, Zach. And then we'll open the floor up to questions. So, Susmita, go ahead.
So, how did the planet growth stop during the accretion phase? I'm trying to understand, although we have a big body or a big Earth's mass, and the chondrules are still forming, so why didn't it capture all the continuously forming chondrules? What happened?
The question, if I got this right, is as the body's growing, why didn't it capture all of the newly formed concepts?
Yeah.
Huh?
Yeah.
Well, to answer that, I'm going to turn it back to you because you know this better than I do. I think your explanation is that there's a certain capture efficiency, right? Which is less than 100%. And when Susmita has gone through this and done the capturing through time, we don't get all of it. What is the fraction that you get? What's your prediction?
Oh, you mean the,
Pebble capture efficiency.
it was between 20 to 60%.
20 to 60% capture efficiency. So we're forming bodies, and again, we're not saying we're making Earth. We're making protoplanets that are, let's say, a third to half, maybe even 3/4 of Earth size. And Jupiter has been argued to be an argument against Pebble accretion because it starves the inner solar system of pebbles. But we're showing, I mean, it's proven that the chondrules continue to grow and that there is probably some leakage across Jupiter. And if we didn't have Jupiter, we'd end up with super Earths, right? We'd have a runaway growth and planets would be too big. So it actually works, which it should if it's real. So, I think does that explain what you're saying? Okay, good, thanks.
Any other questions?
Yeah, there's one.
All right, go ahead, Steve.
Does Pebble accretion work with the other inner planets, Mars and Mercury?
Well, we don't have the composition, of course, of Venus. Mars is pretty darn small, and was probably starved by Jupiter, but it's also early form, we know that. In terms of the relative sizes, I think you've done some rough calculations, Susmita, and it shows that it's certainly reasonable. So Mars and Earth and Venus are about the same size. If they're both in the chondrule forming region, they should grow similarly in size. And who the hell knows with Mercury? It's got this giant iron core and it may be dismembered, just a fraction of what it once was. So I don't know. It's a avenue for future research for sure.
Okay, it looks like we have a question from online. Kevin?
Hi, can you hear me okay?
Hey,
Yeah, we got you.
Hey there, Kevin.
Hi, Zach. Really, really excellent talk. Thank you very much for that.
Thank you.
Yeah, there's an awful lot to like in this model. I had one question and then a comment. So
All right.
my question regards the impactor, also known as Theia in some circles, and the proto-Earth. Do they incorporate the same proportion over time of the pebbles? And if so, that would be a very good thing, right? Because that would explain a lot of the isotopic similarities.
Yeah, well, that's a great question, of course, and I don't think it's one maybe we can answer, or certainly not now. But given the fact that this is occurring really fast in just a few million years, I don't see any reason why you couldn't form more than one seed mass at the same, essentially the same orbital distance, right? And then they're growing really quickly. So you don't need tens of millions of years with multiple collisions to grow these things. They could be in relatively stable but opposite orbits and grow, right? And then ultimately collide into each other. So that may be a solution, and then it explains all the isotope problems.
Right, right. I think that's very interesting. My comment regards the magma ocean ingassing,
Yes.
which I think is also very interesting. But I think one needs to pay attention also to the nitrogen isotopes, because we know that the solar nebula, right, the sun is very, very different from what we're breathing now. And this may be a result of further evolution of the atmosphere, atmospheric loss and so on. But I think it's something worth considering in your models.
Yeah, it is something we have done. I didn't talk about it. We have a paper for all of the noble gases and the inert gases, including nitrogen. And we have concluded that the light ones, hydrogen, helium, and neon, are predominantly sourced from the nebular ingassing. And nitrogen, with its weird isotope composition, is coming primarily from enstatite chondrites. And then xenon and krypton are coming from cometary material.
Right.
That's our estimate, and we're able to fit all of the concentrations and isotope anomalies this way. One of the biggest difficulties is actually hydrogen. Because of its nebular hydrogen, it's going to be really a high proportion of
Right.
protium as opposed to deuterium. But if we have a significant loss of hydrogen as, say, H2, a loss by hydrodynamic escape, or even better, atomic hydrogen, it's ionized, then we can draw the isotopic composition of the Earth up to close to what we believe the mantle value is.
Right, right. I think that would work for hydrogen. For nitrogen, there's not much nitrogen in the pebbles, right?
Yeah.
So that is something to think about, why you wouldn't start off with very, very isotopically light nitrogen. And maybe you could explain it by atmospheric loss, but it's something to think about, in the models.
It's interesting, Kevin, when we did this work, I found that we have like a real orders of magnitude deficit of nitrogen to the Earth from nebular ingassing. And it was kind of like, oh, shoot, this doesn't work. But the sourced from chondrites, and with reasonable estimates for how much of that there is, it supplies nitrogen, but it really doesn't affect the other rare gases very much. There's just so little, of the krypton and xenon, for example, and there's some from argon perhaps, but the lighter ones are probably supplied by the nebular ingassing, and nitrogen just perfectly comes into agreement with the present day values and isotope compositions by having this later addition of echondrite-like material.
Okay, thanks.
I'll send you the paper.
Great.
Any further questions? Go ahead.
Is this model, does this model have like a limit in space? Like if there will be, in terms of regions in distance, will this be if this model happen in other areas of the universe?
Yeah, so the question is if it happens in different regions of the solar system. And it was originally developed actually for the giant planets. because Jupiter was real tough to make that big that fast. And it works very nicely for Pebble accretion to make Jupiter large enough so that it reaches a mass that can actually incorporate, the nebular gas itself. It has to be giant for that. So it was originally proposed and has been studied mostly for giant icy bodies. And the terrestrial stuff is more recent and people have been less willing to embrace this, but it's pretty well established, I think, for the outer, larger bodies.
And then is this something we can expect in other solar systems?
It's just physics, right? So it would be better to say, is there any reason why it shouldn't be in all bodies? And, we saw a picture of young nebula from the ALMA telescope. And there are rings in there and regions, and it kind of fits, yeah. I mean, I think it's probably pretty universal.
Yeah,
Depends on the size of the star, of course. I don't know for, big stars, but these are T-Tauri-like stars that we're considering.
yeah, the young protoplanetary disks are huge reservoirs of pebbles. Like, we have evidences of millimeter size
Yeah.
pebbles there.
Right, okay, so what Susmita said for online is that looking with our telescopes at other similar star sizes and nebula and young star systems, there's pebbles, it's just ubiquitous. So yeah, it kind of has to happen, right? It really should.
All right, any final questions, comments, concerns? Well, Zach, thank you so much.
Thank you.
And then before we head out, just a real quick announcement. Next week, we'll have Thomas Coyer from Lawrence Livermore National Laboratory talking to us about chronology and the wonderful stuff they're doing in Livermore. So please tune in next week. But thank you guys so much for coming today. For those that are here, grab some more pizza before we head out. And for those online, we'll see you guys next week. Have a good one. Thank you.